Hello, this is Ki-young Son from KAIST, South Korea. My research topic is signal integrity analysis of high-speed channel considering thermal distribution. This research is focused on temperature-dependent signal integrity analysis of high-speed channel considering mean value and standard deviation of channel temperature profile. This is contents. First, I briefly introduced about why signal integrity analysis considering temperature is needed, then talk about the model of high-speed channel with thermal distribution. Next, temperature-dependent signal integrity analysis of high-speed channel considering mean value and standard deviation of thermal distribution. Finally, conclude this research presentation. Okay, this is introduction. As artificial intelligence, big data, and cloud computing developed, technical trends require high bandwidth and high computing performance continuously. To maximize operating efficiency, computing system demands much higher computing performances. Therefore, this demands naturally increasing the power density of computing system and cause lots of thermal issues. The dominant thermal issues of high-performance computing systems are mainly caused by three reasons. First, thermal coupling from application processor AP to nearby components. Almost of cases, the AP has much higher power density rather than other components. Therefore, thermal coupling from AP increases temperature of nearby components. Second, increasing trends of memory power consumption. Not only AP, but also the memory also has increasing power consumption trends due to higher bandwidth. Finally, voltage regulator module, VRM, equalizer, and other additional integrated circuits which needs for operating system consume lots of power. Especially, VRM consumed about 10% of graphics card, so it generates lots of thermal issues of computing system. Therefore, due to those reasons, high-performance systems have various temperature-dependent electrical issues caused by thermal issues. From this slide, I'll talk about the temperature-dependent electrical issues on computing systems. In AP, it adjusts thermal issues by algorithmic method thermal throttling. Though thermal throttling can cool down computing system by lowering clock speed, but it causes computing performance degradation. Not only performance issues, but also there are signal integrity issues due to insufficient thermal management. Increased temperature changes the electrical characteristics of overall computing system's components. Specifically speaking, increased temperature reduces mobility and threshold voltages, then it degrades driver strength. Then increased temperature caused material properties changes too. Eventually, those things cause signal degradation on off-chip high-speed channel and skew degradation on on-chip global interconnections. In this research, we are focused on signal integrity performance degradation of high-speed channel due to temperature. Due to the hotspot of AP and memory, the temperature of computing system rises. The increased temperature affects the loss of channel. Therefore, temperature-dependent signal integrity analysis of high-speed channel is important design point because the heat of integrated circuits spreads to the channel. Generally, the loss increases as the temperature increases. As you can see in light figure, high-speed channel design without considering operating temperature is expected to be under-engineered. On the other hand, it can be over-engineered when considering the thermal distribution as the uniform junction temperature value. The loss considering operating thermal distribution of channel is made located between both insertion loss considering room temperature and junction temperature. Therefore, SI design considering operating thermal distribution is required for the high-performance system design. From now on, I'll talk about the model of high-speed channel with thermal distribution, such as the channel model, temperature model, and temperature-dependent electrical properties. The target application of this research, temperature-dependent signal integrity analysis, have been determined with considering channel for high-performance systems. Therefore, PCB and silicon interposer channel are chosen in this research. The feature of PCB channel is long length and LC dominant characteristics. And the feature of interposer channel is short length and RC dominant characteristics. Furthermore, we analyzed both microstreamline and streamline of each applications to analyze each temperature effect on signal integrity. This slide shows the design stack up of target applications, PCB and silicon interposer with physical dimensions. PCB and interposer stack up are designed considering 50 ohm matching and routability respectively. The lengths of the designed PCB and silicon interposer channel are 100 mm and 5 mm respectively. In this research, we analyzed microstrip and streamlined high-speed single-ended channel as mentioned before. PCB channel are composed of copper and PCB dielectric materials, and interposer channel are composed of copper, silicon nitride, silicon dioxide, and silicon. For temperature-dependent signal integrity analysis, it needs temperature-dependent electrical properties of those constituents of both target applications. From now on, I'll talk about the temperature-dependent electrical properties of constituents of both target applications. First, the PCB dielectric. The above table shows the PCB dielectric's relative permittivity and loss tangent considering temperature. Those tables just shows the value on specific temperature, therefore we assume the function of temperature-dependent dielectric properties by using linear least square method. Then the copper and other constituents of target applications are shown in the middle of this slide. A brief summary of temperature-dependent material electrical properties. As temperature increasing, conductivity has decreasing trends and dielectric constants has increasing trends. Furthermore, in this research, we ignored the physical elongation effects due to increasing temperature because in this temperature range, the elongation effects are quite small. This slide shows the cases of simulated thermal distributions. In this research, we focused on the mean value and standard deviation of thermal distribution along high-speed channel. Therefore, we constructed the 6 kinds of cases. The left 3 models, case 1, 2, and 3 are for analyzing the mean temperature effects, and the right 3 models, case 4, 5, and 6 are for analyzing the standard deviation effects on signal integrity performances. Those thermal distribution models are formulated by normal distribution formula. The model 1, 2, and 3 has different mean temperature and same standard deviation, infinite value, for analyze the effect of mean temperature, and the model 4, 5, and 6 has different standard deviation and same mean temperature, 60 degrees Celsius, for analyze the effect of standard deviation. Moreover, model 4, 5, and 6 are formulated with high temperature of both TX and RX side considering the practical situations. The TX and RX are usually attached on integral circuits which has higher temperature. And the constant value A and B of thermal distribution model is depend on the value of the mean temperature of thermal distribution. From now on, I'll talk about the temperature-dependent signal integrity analysis. Firstly, signal integrity analysis of high-speed channel considering mean temperature of thermal distribution. Before signal integrity analysis, this is the brief introduction of insertion loss configuration. The insertion loss consists of conductor loss and dielectric loss. The attenuation from conductor loss, alpha conductor, is proportional to the metal resistivity and dominant at low frequency range. And the attenuation from dielectric loss, alpha dielectric, is proportional to the dielectric properties and dominant at high frequency range. And this is the signal integrity analysis of PCB channel considering mean temperature of thermal distribution. This one is the simulated insertion loss of PCB microstrip channel, and this one is PCB strip channel. The both microstrip and strip channel shows the increasing mean temperature degrades the insertion loss at high frequency range. At low frequency range, due to the PCB channel is edge dominant, the alpha conductor degradation effect is shown small. At high frequency range, due to the PCB dielectric properties have increasing trends along with temperature, it showed that increasing temperature causes alpha dielectric increasing. This is the signal integrity analysis of interposer channel considering mean temperature of thermal distribution. This one is the simulated insertion loss of interposer microstrip channel, and this one is the streamline channel. The both of microstrip and strip channel shows the increasing mean temperature degrades the insertion loss at overall frequency range. Due to the silicon interposer channel is arch dominant, the higher copper resistivity as increased temperature causes alpha conductor increasing. Furthermore, at high frequency range, the higher relative permittivity of silicon dioxide caused increasing alpha dielectric. Therefore, the high mean temperature caused the increasing insertion loss of the high-speed channel. This slide is the summary of mean temperature effects on insertion loss of high-speed channel. The table shows the insertion loss and increase rate due to mean temperature increasing at 100 MHz and 10 GHz. At low frequency range, insertion loss increase rate has no big differences between microstrip and streamline at both high-speed channel. However, at high frequency range, insertion loss increase rate of strip channel is larger than microstrip channel. This is because strip channel has more ground area compared to microstrip channel. The alpha dielectric is proportional to capacitance, which is proportional to dielectric constants. Therefore, the conductance increasing effect due to the increase in dielectric properties with higher temperature is larger on strip channel than microstrip channel. This slide shows the differences of high-speed channel insertion loss between 40 degrees Celsius difference cases at broad frequency. This is the insertion loss difference between PCB microstrip and my strip channel. It shows quite similar values over the broad frequency considering standard deviation. And this is the insertion loss difference between interposer microstrip and strip channel. It also has similar insertion loss trends due to standard deviation of thermal distribution with PCB channel. Difference of simulated high-speed channel insertion loss between 40 degrees Celsius difference cases show the insertion loss increase rate due to temperature increasing are uniform at 20 degrees Celsius to 100 degrees Celsius range. In other words, the dB scale insertion loss tends to increase linearly with temperature. Therefore, the temperature and alpha have a linear functional relationship due to the insertion loss formula, which shows the insertion loss is proportional to the alpha. And then I'll talk about the signal integrity analysis of high-speed channel considering standard deviation of thermal distribution. Then I'll conclude this research presentation. In this slide, it shows the cascading segment channel to analyze the signal integrity of high-speed channel considering thermal distribution. To analyze the insertion loss considering thermal distribution with various standard deviation, we simulated numerous segment channels considering each temperature along thermal distribution and cascaded them. More details are on the next slide. Cascading segment channel can be expressed as left figures by using ABCD parameter. The ABCD parameter of channel are composed of attenuation constants and phase constants. The segment channel's characteristics can cascade by using ABCD parameter. The cascaded ABCD parameter is made by multiplication of ABCD parameters of segment channels. As the right side equations, the A sum can be expressed as the combination of Zi, Zi plus 1, Yi, and etc. If the total amount of segment channel n go to infinite, the alpha sum can be expressed as the summation of alpha I and alpha I plus 1. It means the cascading segment channel considering thermal distribution shows the cascaded alpha are proportional to sum of segment alpha. It can be also proven at the B sum, C sum, and D sum. As mentioned earlier, the temperature and the alpha has a linear functional relationship. Therefore, the cascaded alpha, which considering the thermal distribution, is quite similar with alpha considering mean temperature of thermal distribution. From the next slide, the simulated insertion loss of high-speed channel considering standard deviation of thermal distribution, which shows the cascaded alpha has quite similar values with insertion loss considering mean temperature. This is the signal integrity analysis of PCB channel considering standard deviation of thermal distribution. This one is the simulated insertion loss of PCB microstrip channel, and this one is PCB strip channel. The both microstrip and strip channel shows the quite similar insertion loss with various standard deviations, and it shows the insertion loss considering thermal distributions are dominantly related with mean temperature. This is the signal integrity analysis of interposer channel considering standard deviation of thermal distribution. This is the simulated insertion loss of interposer microstrip channel, and this one is the strip channel considering various standard deviations. Both simulated insertion loss of target application considering thermal distribution verified that the cascaded alpha considering thermal distribution are quite similar with insertion loss considering mean temperature as mentioned before. Therefore, those results show that it is sufficient to only consider the mean temperature for temperature-dependent insertion loss analysis of channel without considering the standard deviation. Okay, this is conclusion of my presentation. High computing performance system causes SI performance degradation due to thermal issues by much higher power density. Therefore, SI design of high-speed channel considering thermal distribution is essential. Mean temperature directly affects to SI performances, and even if standard deviation is different, it has quite similar insertion loss with same mean temperature cases. In addition, when designing the RC dominant channel and streamline channel, it needs more attention to thermal distribution effects on SI performances. Thus, SI design considering operating thermal distribution is required for designing high performance system. This is the end of my research presentation. Thank you for listening, and if you want some more details, contact me by the below email or see my paper. Thank you.